Okay, welcome everybody. We're going to start the first afternoon session. And as we start, we'll have sort of people come in and fill sort of the ranks. So let me first introduce myself for those who do not know me. My name is Axel Drees. I'm a professor in the Department of Physics and Astronomy, and I'm also the chair of that department. And it is my distinct pleasure today to introduce my colleague, Dominik Schneble, who is giving the first talk. Dominik is an expert in preparing macroscopic atomic quantum systems at ultra-cold temperature, which are Bose-Einstein condensates, and then manipulating them in a way, preparing them that they can be used for quantum simulations. And that's exactly what this session is about, sort of the third pillar of quantum information science, quantum simulations. So, Dominik, please start.
Thank you, Axel, for the kind introduction. And I have to say, after two such great talks, it's really hard for me to follow up. But let me try my best. So, as Axel has said, I'm working on ultra-cold atoms. I'm an experimentalist, and I want to tell you a little bit about analog quantum simulation. It's something that we can do with these systems. And just to start off, let me show here the figure from the European Quantum Technologies flagship report. One of the pillars here is quantum simulation, and that refers, of course, to quantum simulation of real physical systems. And this was a point which was made very prominently by Richard Feynman in 1981 at MIT at this conference, where he said, the rule of simulation that I would like to have is that the number of computer elements required to simulate a large physical system is only to be proportional to the space-time volume of the physical system. I don't want an explosion. And then this famous statement, which I've redacted slightly, nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical, okay? So a famous problem that many people have been thinking about for a long time is high temperature superconductivity, for example, which was discovered in 1987 and has a generic phase diagram shown here, where you have an antiferromagnetic insulator and a superconductor down here. This is temperature, this is the doping level. And despite decades of research, the mechanism for pairing and the high temperature superconductivity has not yet been identified. It's not yet been found. And part of the problem here is that these phases down here are strongly correlated phases of matter which hold a lot of entanglement and quantum correlations in them. So it is very hard to use classical methods to figure out this problem. All right, so now what is analog quantum simulation? I just wanted to basically walk you through the different aspects of quantum simulation. And so if you have a quantum system that's described by a wave function in Hamiltonian, of course you can write down Schrödinger's equation and you can define a time evolution operator, and you can just apply this operator and solve this problem. And this Hamiltonian in here is describing mostly the interactions between the particles in the quantum system, or the interactions, of course, with the outside world. But if these interactions are local, they can be written as a sum over pairs, and then it is possible to write this time evolution operator as a sequence of gates, of local gates, and that's actually that starting point for digital quantum simulation, yeah, that you can basically do that with a quantum computer. The only thing is you need a very large number of gates if you have a very large number of particles. And if you want to be very precise, you have to do this in very small time steps. And so you need a huge capacity for quantum computation and large amount of error correction. Okay, so there's a different way to look at this problem, which is to say, well, I have a quantum system here which evolves. I might have another quantum system which evolves similarly. And actually, if I consider this quantum system here shown in green as a simulator, I can simulate a system. The only thing I need is I need a correspondence between the system and the Hamiltonian. And in this way, I have an analog quantum system here. Often, what I want is actually controllability. So in having this system evolve, I want to vary parameters. And so my Hamiltonian is tunable in the simulator. And in this way, I have an analog quantum simulator as well. I'm taking this distinction here from a paper that is on the archive. It's written by a physicist, an engineer, and a philosopher. And I think this is a pretty good combination. And so they make this basically epistemological model for quantum simulation, which I want to present here and walk you through. So you have your two systems, S and S prime. S, the system that you want to simulate, they call it target. Your simulator is the source. And we have two distinctions here. One is the concrete level. It's basically the system that you have in front of you. And the other one is the abstract level. So on the abstract level, a system is represented by a Hamiltonian. And a system gives rise to phenomena that one can measure using apparatus. And of course, you have predictions for those phenomena on the level of the Hamiltonians. And so, of course, the systems might be different. But to a certain degree, you can approximate the Hamiltonian of your target through an effective Hamiltonian, and you can approximate the Hamiltonian of your source through an effective Hamiltonian. Sometimes it's important to sort of restrict the parameters in your system so that you can sort of be in this approximation, but then you have a correspondence here between the effective Hamiltonians, and that is what quantum simulation is. Okay, and then you can play around and sort of explore what would happen in the real system if you were able to vary the parameters there as good as you can in your simulator. Okay, they make a further distinction, which I think is quite useful, which is if you don't care about the Hamiltonian, you just have two quantum systems, and you compare them, that's called emulation. Yeah? Whereas if you have only Hamiltonian here, not necessarily a quantum system that corresponds to it in reality, that is a simulation. And so you can simulate Hamiltonians and you can emulate systems. Okay, now the advantage of a quantum simulation is that all the quantum information is stored in the system itself. So you don't have to care about carrying that along as you process. It's all happening for you in the real system. And an additional advantage is that any real system has decoherence. Your quantum simulator can also have decoherence if it's not worse than the decoherence of the real system. So you are somewhat tolerant to decoherence in this case. One problem is, because it's an analog simulator and you don't really understand the underlying dynamics, or you cannot analyze them independently, validation is a problem. So it is not really clear per se whether the result of a quantum simulation corresponds to reality or whether it is somewhat a property of the system that you haven't thought about or that might have changed during your simulation. So therefore, rather than having a competition between platforms, one should have a multitude of platforms that can sort of approach the same problem and simulate the same problem independently so that one can compare. So there's a few platforms that I want to mention here. One is the ultra-cold atoms. I'm going to talk about them. We have Rydberg atoms and trapped ions. And we have photons They can be optical photons, or they can be microwave photons. So it's a whole range of systems that can be used for quantum simulation. Okay, but now I want to talk to you about the atoms. So atoms, they have a natural energy, length scale, and time scales. They're listed here for hydrogen atom. So on one end, you have high energy physics that's very far away from that. But the ultra-cold atoms, they are on the other end of the spectrum, as far away from a normal atom in terms of its energy as high energy is. So we're talking about nanokelvins of temperature, we're talking about millimeters per second speeds, and we're talking about sizes of wave functions on the order of 10 micrometer. Okay, you could also think of this in terms of the evolution of the universe. We are here somewhere around 400,000 years with our atoms, and the ultra-cold atoms are basically what you will have in the far future when the temperature goes to 0. Okay, so how does one generate quantum gases, or what is your analog simulator? It's a typical picture here from our apparatus. There are many such apparatus around the world. So you have a bunch of mirrors, vacuums, lasers, a control computer, yeah, and then so it's different techniques that allows you to sort of go as low as you can into the 100 nanokelvin or lower regime. Okay, now there are two kinds of quantum gases that one typically looks at, fermions and bosons, so degenerate Fermi gas and Bose-Einstein condensate, and they by themselves are quite boring, but if you sort of allow for a little bit of energy and you allow for a little bit of variation, there's a whole slew of things that you can do. And actually, the field of ultra-cold quantum gases has been doing quantum simulations for 20 years, if you want to call it like that. So we are going here from nonlinear effects to solid-state physics and even nuclear physics and high-energy physics maybe. And so I want to tell you about two things here, two quantum simulations. One is a classic one. It has been done in many labs. It's from condensed matter physics. And then another one, which we have done recently, where we looked at quantum optics. So the example I want to give you is the simulating a transport behavior in solids, so it's transport of electrons. So I'm going back to this diagram here, which I fell in love with. So let's look at our system. Our system is, let's say, a metal. Can be any metal. We can model that by saying, well, the metal consists of atoms, yeah, and the atoms are bound together, so we are lining them up. This gives us a band, periodic structure with a band structure here energetically, and so that's what we have. This is on the abstract level a representation of this material. Now, I can take a quantum gas and put it in an optical lattice. An optical lattice is just a standing wave of light. If I do that, well, what do I get? I get an optical potential. So-called optical potential is the interaction of the light field with the dipole moment of the atom, which is periodic. And I will have a band structure in there, and I basically get a very similar situation here. Of course, my Hamiltonian is slightly different because the structure, the detailed structure of the system is different, but there is clearly some similarity there. And actually, on the level of the effective Hamiltonian, I can sort of treat my lattice as a series of containers, and I might be, oops, this should actually be an atom here, not a V. So I go from basically from one side to the other with a tunneling matrix element J, which I then calculate based on the detailed physics that I have on these sides. Okay, the bandwidth in my model system I can vary. So the laser intensity by simply making the lattice deeper or shallower. I can change the beam configuration, 1D, 2D, 3D. I can have different geometries, so I can control basically whether I have a bulk, layers, wires, or I can vary the crystal structure. I can introduce disorder, interactions, external forces, spin, and so on. So I have basically a whole playground here available in order to investigate properties in real systems that I could actually never investigate in that detail because I don't have the parameters on the real system size that I can control. Okay, so of course, these simulator materials, if you want, are much different in terms of the length scales and time scales and energy scales involved. Lattice constancy is typically 1,000 times longer, which means that the dynamics is much, much less fast, exacerbated by the fact that I'm dealing with atoms in here, not electrons, so they're much heavier. And so I have basically 9 orders of magnitude difference in the energy, and that means I'm dealing with, again, 100 nanokelvin temperatures and rates on the order of kilohertz for hopping between wells. Okay, most importantly, of course, yes, I have electrons on one side and atoms on the other side, and the electrons are fermions. The atoms can be fermions, but they don't have to be, can also be bosons, so that's a difference. And very importantly, of course, electrons are charged and the neutral atoms are not, but it turns out that's actually not such a big problem because charge in materials that can be screened. Okay, so let me now come to the Bose-Hubbard model. So if I take atoms and put them in an optical lattice, they can tunnel, yes, so I get this tunneling term that we have just seen. But if I have bosons, I can also put 2 such atoms in the same place. Yeah. It wouldn't work for fermions because of the Pauli principle, but for bosons, I can do that. And so that gives me an energy cost, it's just given by collisions, which leads to repulsion, and that's another term in here. Yeah. And for bosons, I can basically write this as the population on the side minus 1 times the population. So if I have 1 there, the term is 0. If I have 2, it's 2. Okay, so the ground state of this model now depends on how big is the tunneling, which wants to delocalize the atoms, and how much is the repulsion. And if I have very strong tunneling or very weak repulsion, the atoms are all smeared out. I can write this as a coherent state. But on the other hand, if I have very strong interactions, I have 1 atom per side. So this is a so-called Mott insulator, which doesn't have any coherence and which does not sort of allow for conduction. All right, so there's a quantum phase transition. I can tune between this by just varying the lattice steps. All right, so how does that look? Well, I have to now define how do I analyze my system. And typically what I do is I put wires on a metal and check whether there's conductance or not. But in these simulators, I have more access. I can actually just turn the system off and then just look at the distribution of the atoms as they sort of come out and spread. And what you see here is a so-called time-of-flight image of an atomic cloud that was released from an optical lattice, and what you see is beautiful diffraction patterns that reveal the underlying lattice structure. Okay, now, yeah, here is also in time again, so it nicely shows you how gravity does its job also as time of flight goes on. So we just pick out one of the times, and now we vary the lattice steps of the lattice that we come from. And what you see is that as we increase the lattice steps, the visibility of this pattern goes away, which shows that we are basically losing the coherence, which means we are starting to localize the atoms. We are going to the Mott phase, and as we lower the lattice steps again, we are going back into the coherent regime. Okay, so these are data from our group. I should say we are just one of many who can do this. The original experiments were done in a group of Ted Henge and Emanuel Bloch at Max Planck Institute. And the first author there was Markus Greiner, who is now professor at Harvard. And actually he has carried this work much further. And some of the most recent work is that they looked at Fermi gas. There you have now a system which has introduced, where they have introduced a spin, so two internal states. And they put this under so-called quantum gas microscope. This is something that they developed about 10 years ago, where you now can look in situ where the atoms are, and you can look at spatial ordering directly, so that you are not limited by the coherences that you see in time of flight, or by more demanding methods that you might need to apply there. So what you see here is the Fermi-Hobbit Hamiltonian at a very low temperature, and what they observed here was an antiferromagnetic ordering of the mod insulator, which is very much in this regime where it becomes very interesting. And so there's actually a rather large number of groups who are now also looking at this and racing each other. And of course, the holy grail is then to understand what's really going on there, whether this, by doping, becomes a superconductor when it's cold enough or not. Okay, so that was the example on condensed matter physics. Now, let me give you a totally different example, which is a work that we did recently here at Stony Brook, which is a simulation of the emission of photons. Now, that doesn't sound like something that needs to be simulated, but actually, there are regimes which are very much exotic and which cannot be accessed yet with systems that emit photons, but which nevertheless need to be explored, and we were here in a situation to be able to do this with a system that emits atoms instead of photons. Okay, so what is the model of spontaneous emission? In QED, well, this was started by a famous physicist, Paul Dirac, who wrote down a Hamiltonian for the coupling. What do you see in this Hamiltonian? Well, there are operators in here, lowering and raising operators. This one here brings the atom from the excited state to the ground state, so it decays, and out comes a photon with momentum k. All right. The strength of this process is given here by this prefactor. This is the dipole moment of the atom interacting with some electric field. And what is this electric field? It's the zero-point field of the vacuum. Yeah? So basically, the atom interacts with the vacuum, and through this interaction, it can emit a photon. Okay, and so this was actually analyzed by two other famous physicists, Victor Weisskopf and Eugene Wigner, who solved this problem by just writing down an ansatz for the wave equation and plugging it in there. And what they found was the transition rate for the decay, assuming that the decay is exponential. Okay, their assumption is generally valid because the line width of the transition is so much narrower than the transition frequency. So it's basically like a needle here, above the ground. And so that are the conditions which give rise to exponential decay, which is usually what you see. However, one might have stronger coupling so that the transition becomes wider and reaches the energy itself, the transition energy itself, or one might have a dispersion relation here which has a gap. Or there might be a dispersion relation which has just a single state. Now, of course, we know, or many of us know, these scenarios. This is just cavity QED. You have a single mode and an atom coupling to that single mode. Yeah? And then here, this is another regime which is interesting. This is so-called waveguide QED or photonic bandgap QED. So you put an atom into a photonic bandgap material, which is basically just a periodically modulated refractive index in space. And if the emission energy is in a bandgap, the atom will not emit, but maybe something else happens. And so there were predictions and also initial observations of a so-called atom-photon bound state, and there were predictions of a decay that is not exponential anymore. Okay, so what's the basic idea? The basic idea is that An atom is basically just a container for a photon. Okay, we're taking a very simplistic approach here. An atom is a container for a photon. The photon comes out because there has been coupling to vacuum, and then the container is empty. We call that then the ground state. Now I can do the same thing if I construct myself an artificial atom, which contains a real atom. There's vacuum coupling. The real atom comes out. The artificial atom is empty. I call this in the ground state. So one can go through this analysis pretty closely, and what one finds is that the wavelength of the light that comes out of a normal atom is replaced by the de Broglie wavelength of the matter wave that comes out of this artificial atom. Okay, so what do you need? We need atoms which have two internal states. We need a microwave coupling between them to perform Rabi oscillations, so it's basically a qubit if you want, even though it's not really addressable. And you need a potential which does different things to these two states. The potential that we have is a potential which acts on the state down here, so you basically see potential wells, and it does not act on the blue state. So this means you can be trapped in here. This is your container. One of those wells is your container, and then you might sort of emit into the free level. Okay, so we can do all this. We put these things together, and we end up, turns out, with a Hamiltonian that is just the Dirac Hamiltonian again, except that now the coupling is tunable, and the emission energy is also tunable. And so we can, among other things, we can look at this strongly coupled regime, and we can look at the regime where we are in the band gap. Okay, so we see, for example, exponential decay, but we also see non-exponential decay, oscillatory decay. This is a case where a photon, if you want, would leave an atom and then come back in. So the attraction is too strong, or the coupling is too strong. We can, well, there's a slight modification here. This is a whole bunch of them. This is an array, so this is an excited state emitter, ground state emitter. They couple to each other. We see modifications. We understood all that. We can also look at the radiation that comes out. And the radiation comes out, you see here, it's in time of flight. These are two blobs. We can plot them here, and then we can vary the energy here of the excited state. And what we see is a beautiful dispersion relation, just as one expects, with energy conservation. Now, there's also something at negative energy, as you see. What is this? Emission at negative energy. Well, if you think about this, momentum is square root of the energy, so if the energy is negative, momentum is imaginary. So this means that the wave that comes out is evanescent. It's a bound state. So this is exactly the bound state that was predicted, and we can see this here in a careful analysis of the momentum distribution. You see here the blue data. This is, if you sort of go through here, and the red curve is not a fit. It's a comparison to the analytic model that we were able to make for that state. So we were able to identify this state based on its momentum footprint. And so you see this is an artistic illustration of how this looks like. This is how it looks like in reality. You have the bound atom in the well, and then it's surrounded by this state. Okay, so there are optical relatives for this. So we have basically performed a quantum simulation of the Weisskopf-Wigner Hamiltonian, but also we have performed a quantum emulation of a system that exists for photons. Here you see two examples. One is a one-dimensional photonic band gap guide, where you have atoms sitting on top, and they are emitting into the guide, or being coupled into the guide. The problem in these systems is that they are still coupled to the surrounding vacuum. So the amount of coupling that they can achieve here is not comparable to what we can do. That's why they're not able to see this oscillatory decay. Another system here is based on transmon qubits and microwaves. In this case, the situation is cleaner. They have indications of a bound state and of interactions between transmon qubits mediated by bound state, but of course, they cannot see that in anything else than the spectrum. So we were the first ones to sort of see the spatial structure. And so in that sense, one could now say they should emulate us, or we can emulate them. It's basically two systems which are more or less comparable. Now, the applications that they envision here is that they basically want to engineer photonic interactions that are coherent and go over long distance. And so using bound states which have a divergent decay length is basically ideal for that. Yeah? And so we take the approach that with our quantum simulation, we basically wanted to understand something about the nature of spontaneous emission. We wanted to understand the implications of the Weisskopf-Wigner model, but we could, of course, equally say we have here another platform in which some of those things that they plan to do can also be done. Okay, and so with this, my time's up, and I thank you for your attention.
So we'll start the discussion by the panel members introducing themselves, and we start from the far end of the table.
Okay, so good afternoon. I'm Leon Sterngas. I'm with Electrical and Computer Engineering Department. I'm part of the optoelectronic group. So we work with semiconductor lasers. We have quite extensive operation here at Stony Brook. We have full in-house technology, can grow lasers, photodetectors, new materials, narrow gap materials, and recently we start working with devices that can emit optical frequency combs, and that actually led us to think about the utilization of the four-wave mixing in non-external silicon photonic-based chip scale devices to enhance the bandwidth of the optical frequency combs, and that actually led us to thinking that essentially the same system can be bright source of the entangled photons, which can be utilized for this new exciting field. And since our lasers are working at longer wavelength range, we have advantage and disadvantage compared to silicon devices. We can actually utilize silicon as a material which has much higher nonlinear coefficient compared to other silicon photonics materials, and we can hopefully, if we can eventually deliver those entangled photon pairs in a chip in a compact way, because our lasers is against very small semiconductor lasers. If we hybridize them with this, we can actually bring those entangled photons on a chip, and hopefully with all functionalities of the silicon photonics, with all possible resonators, filters, and the photonic crystals, which can actually offer some possibilities to design the dispersion of the material of the system, we can actually try to make a contribution in the field. And especially if you consider the transport of these single photons through the waveguides, it's probably more or less directly related to the discussion of this simulation. Yeah, so, thanks.
Thank you. My name is Sasha or Alexander Ebanov, and I am a professor at the Department of Physics and Astronomy. And I have two messages to deliver. I think it's one is about my research, and another is much simpler one. I'm also a deputy director of Simon Center for Geometry and Physics, and we are very happy that this initiative is being developed. Simon Center supported the few workshops and programs in quantum computations and then in topological phases of matter. And Simon Center runs about 10-15 workshops per year, which is 1 week workshops, and longer programs for 5. And we are open for proposals, so welcome to propose some activities And the topic, we usually like to bring physicists and mathematicians together at Simon Center, and of course quantum information processing is one of the fields which is suitable for this. So that's a simpler message, and I myself is interested in theoretical condensed matter, in particular in quantum strongly interacting systems, starting from electron systems like high temperature superconductors, quantum Hall effect, but also cold atoms, and so on and so forth. And what I want to say is I want to emphasize some part in this newly developing field, which is risk-free investment, unlike building quantum computer where you can eventually fail due to decoherence or doing something partial. There is actually a risk-free part, which is the feedback of all these developments on fundamental research itself. So this is what I want to say. It already sounded during the previous discussions. For example, thinking about quantum mechanics in terms of information processing might give us new understanding of quantum mechanics, and having different understandings from different angles is always important. But another is more direct, like Dominik, thanks Dominik for a very nice presentation, explained, for example, that he in his lab is simulating Bose-Hubbard model, essentially putting atoms in the optical lattice, instead of a Hubbard model already existent in, for example, in descriptions of high temperature superconductors, where you put electrons, well, electrons are put by nature and in a square lattice type of arrangements. So one might think that why would I need to simulate the same model? We already have it. Go take high temperature superconductor and measure. Well, first of all, in Bose condensation systems, they have much better control on some aspects of this system, so they can do more in various things. But most importantly for me is that it raises a lot of new questions which were irrelevant or semi-irrelevant for electronic systems. For example, you have times of the order of seconds or milliseconds instead of femtoseconds, so you can actually ask questions about time dynamics of these Hubbard models. You have to solve time-dependent Schrodinger equations, while in condensed matter, very often we just solve stationary Schrodinger equations, and so on and so forth. There are many such examples, and I think that while you might eventually not build the scalable universal quantum computer, I'm not going to be too skeptical about this, but even if you don't do that, you will discover a lot of things about quantum physics, and quantum mechanics is one of the most beautiful and most fundamental discovery of humanity. So it's really important part of this research. Thank you.
Yes, I'm Derek Teeney. I'm also a professor in physics department. I work on, I'm a nuclear theorist. So my research largely is involved with the physics of the Quark-Gluon Plasma, which is the state of matter that is created when you collide two heavy nuclei at high energies. It was also present during the early universe for a considerable length of time. So quantum simulation plays a role here because we would like to understand the kinetics of these gauge theories and how they equilibrate and so forth. And a lot of the issues, I mean, in weak coupling, you can sort of analyze the kinetics, and a lot is known about the quasi-particle structure and radiation and how that contributes to the whole equilibration process. However, as the coupling gets strong, for many of the reasons that Dominik was talking about, I mean, quasi-particle widths get large. The radiation plays you're sort of constantly emitting radiation, or much more than you would have imagined, and that sort of interferes with the process. So that gets really difficult to analyze. And so here, any kind of information about the real-time dynamics of such systems really can play a big role. Now, there's been a lot of examples already. I mean, so this is a different field of nuclear physics, but cold nuclear physics. So I was talking about hot nuclear physics there. But in cold nuclear physics, there's, of course, fermions with large scattering length, which is also a very strongly coupled system. And so that system, as far as I know, was first studied or thought about in the context of nuclear matter, neutron matter. And so it's a great example where simulating fermions near unitarity can really give guidance, okay? Now, coming back to the Quark-Gluon Plasma, so many of the things that Dominik was saying, I should talk to him more often, what really come up all the time, and questions about how good are quasi-particles, how long can you use any of this stuff. So it's really a good example where you could look at this non-Markovian decays and wonder if that kind of stuff goes on. Personally, there are so many questions about Quark-Gluon Plasma. It's nice to have model systems, even if they're not the real system, where you could see whether these are true. So it's not really a simulation, it's just a different system which has some similarities. And you can use that for guidance towards theoretical calculation, okay? So, well, I think I'll leave it there.
Okay. Yeah. It's Mike McGuigan again from the Computational Science Initiative at Brookhaven Lab and the Quantum Computing Group. And so I just want to echo the last two speakers, the cross-cutting nature of this quantum simulation from condensed matter to nuclear physics. I'm part of a collaboration on quantum field simulation and quantum gravity simulation and quantum computing. And this is something that, when you think of it, everything fundamentally that we know of is based on quantum fields. And each point in space-time is a degree of freedom in that realm. So if you try to calculate something like entanglement entropy, you get incredible amounts of entanglement because there's just so many degrees of freedom at one point. It actually diverges like entanglement entropy. So this analog simulation, it seems like an ideal tool to study these condensed matter systems, high-energy quantum field systems, and even early universe cosmology, including gravity, because of the scale of the system that potentially could be achieved. For example, just a 128 cubed lattice, which would be a crude approximation to the universe. There's like 1 million sites right there. Each one of those would be a degree of freedom. And if you want to represent a boson, which has an algebra which requires an infinite dimensional algebra, and you want to discretize that, you're really talking an incredible amount of qubits that would be many decades away. And when we do physical simulation, we're trying to match with experimental data, and we're trying to guide our most advanced theoretical models. We use the most advanced tool we can. So this is in lattice field simulation, for example, they design their own computers, their own processors, their own interconnects, whatever they can do to get at the physics at the earliest possible time scale. Because today I might be able to do a quantum field calculation on a laptop for imaginary time, which was done 20 years ago. But they wanted to know the answer 20 years ago because that's when they needed it to guide the experiment. So if we want to do things today, I think this is an excellent platform to investigate.
Okay, thank you. So let me just add that I'm myself an experimental nuclear physicist. I'm not really involved in quantum information science other than in my role as chair of the department. So I'm somewhat the experimental counterpart of what Derek said. We work very much in the same field. But I find it very intriguing that you can sort of set up an atomic system that is equivalent to some other quantum system and then let that system tell you what the solution is.
I mean, one thing that we run into sometimes is that the Hamiltonians that correspond to the real system are beyond our capabilities. So the question is whether it would be possible or make sense to carve out a piece of a Hamiltonian and then analyze that, or whether it's the full system that one wants to analyze.
Mm-hmm.
But this is what theories do anyway. They simplify, yes. Right?
Yeah, so the simplification upstairs, going from the Hamiltonian to the effective Hamiltonian, that's a series. Yeah.
That's right, and the ability to turn off certain terms and turn on certain terms, that's something you don't have in the physical system. But in the simulator, you might be able to have that. And then you can see the importance of different terms, like the importance of the gluon, for example, relative to the quarks, and things like that in the equation of state. So, that's a degree of tunability. It doesn't have to happen during the calculation, but, you might be able to set it up different ways to investigate the strength of different terms.
Okay, so let's open it up for questions from the audience. Yes, Vladimir.
Dominik, you mentioned Fermi Hubbard. Can you build it in 2 dimensions or in 1 dimension, or both?
So the measurements were done in 2D, but there's no reason that they shouldn't be able to do it in 1D.
1D might be interesting because there are many conservation laws. The system will not thermalize. So
That's very possible. It's just
exciting.
that from an experimental point, it is very easy
to do one dimension, right?
to go to one dimension. It's
Thank
not
you.
so easy maybe to go to 3 dimensions due to the geometry of the setup that they're using, even though there's ways around that.
Right, and one other thing, as Vladimir is aware of, in one dimension, there's a lot of exact solutions that we
Yes.
have. That'll be a great way to test, the answers of the quantum computer, guide us what the answers are. And these exact solutions go beyond even what we can do on the supercomputers because they're mathematical based.
I mean, that has been our approach to do 1D physics. I didn't mention that, but over the past decade, most of our experiments were restricted to 1D, and for us it was kind of nice to be able to compare
Right.
with a theory, simply to validate our approach, because as an experimentalist, it is very easy to sort of fall victim to a drifting parameter somewhere or to something that one has overlooked. But if there's a theory that one can test against and build confidence, then later one might go to higher dimension. But it's definitely a good thing to have exact solutions that one can compare with.
Okay, more questions?
I have to apologize first. Maybe this question is stupid. Maybe I have missed some of the slides. So all of these like simulations or emulations talking about, are they actually still carried on the classical computers or actually using the nowadays available quantum computers? Or if they haven't been using the quantum computers, what do you expect if you switch to quantum computers? Thanks.
So far, these simulations can only be done in an analog way. It would be good once quantum computers become more powerful to perform a digital quantum simulation and then compare the analog with the digital one. But so far, it's 3D. For example, it's analog, sorry. For example, the emission problem that we have is the theory, our simple theory was for one dimension, for one emitter. But in this array, we have many emitters, and we can have many emitters at an excited state, and there's all kinds of interesting effects that can appear once one has more than one, and which cannot be calculated, especially not in the Markovian regime. So that's a frontier where our system is actually very interesting for theorists also.
Yes, please. Do you have a comment?
So it sounds like your analog simulation doesn't have the coherence problem. Could you comment?
Well, at least it doesn't have a decoherence problem to the degree that it would completely kill the effects that we observe. Yeah. It's of course hard for us to quantify how much decoherence there is when we don't have a theory that we can compare to. But at least in some of the examples that we have, we are able to compare with calculations, and the result is very good. So we assume that the decoherence is very small.
Yeah, please.
I wonder if you can combine sort of the last two approaches. So suppose you can only simulate what you actually know. So suppose you're not sure of the Hamiltonian. Is there some way that you can sort of evolve and do a sort of a comparison with, once you actually succeed in doing this, and try and narrow down what the parameters of the Hamiltonian are? So sort of do a quantum machine learning version of the quantum simulation.
That's an interesting question. Maybe, but what I can say is that that's actually what happens quite often, that you do something in the lab and you really don't understand what is the Hamiltonian that gives rise to this behavior, and you're just playing around and trying to sort of get a feeling how things connect together, and then in the end you extract the Hamiltonian from somewhere, and then you try to sort of restrict your parameters such that you can converge towards it. Yeah? But of course, your question also implies is there maybe another quantum system where the Hamiltonian is also not known and which you're now trying to imitate? And that's a very hard problem because you can't look into the other system unless, or let's say this way, the Hamiltonian is already your understanding of the system. And if it's not there, then and you cannot perform the same kind of measurements on that system, then it's very hard to sort of find convergence.
To the theorists, for Quark-Gluon Plasma, is there a sort of obvious interaction Hamiltonian that would be kind of interesting to investigate as a toy model for quantum simulation?
Okay, so obviously the non-abelian symmetry plays a big role, okay? But let's start with somehow the emission of radiation. So one of the things that happens in the Quark-Gluon plasma is that you have energetic particles who go through the Quark-Gluon plasma and they radiate, okay? And this sort of collinear radiation then suffers multiple interactions as it sort of leaves or traverses the plasma. And we have a fairly good perturbative picture of how that works, but you could be worried when in different regimes where the scattering becomes very rapid, okay, what that does to the emission process and so forth. So that's a perfect example, just listening to what you were saying, of where you could try to simulate that, okay? And so at least for photon emission, this is something you could imagine. Now, for the real case, you're actually interested in gluon emission, right? And then you have this problem that somehow what you're trying to radiate will also experience collisions, right? And then you should take that into account. So putting in some aspects of the non-abelian emission of radiation, that sounds difficult, but who knows, okay? At least you could start with photon emission that was already used as an indicator for the Quark-Gluon plasma. In particular, Axel has worked on measuring that. And so somehow measuring that process, understanding that in different model systems is actually a very excellent example of also when the plasma is equilibrating of the kind of things you could try and study.
Okay, there's one more question here.
This is maybe not directly addressing your analog model that you were looking at, but generally the idea of using an analog approach. One of the big problems that you have when we do simulations is the process of integration and trying to make sure something is symplectic or unitary when you're performing these calculations digitally, and this is always a challenge that we faced with. I wonder, has any thought been given to developing analog approaches that would be both unitary and symplectic and have all of this stuff built into it, so that this would address a lot of the problems that people who are doing simulations would like to have.
Yeah, I think that's one of the key advantages of the analog, is that you have the E to the IHT, and the T is essentially continuous. So you don't have the same kind of energy not being conserved problems you have when you try to do this on a classical computer. So it's one of the advantages, I think, of the analog system.
Well, also in terms of unitarity, they basically fight losses, which means that they're trying to make their evolution unitary. So it's the same problems, but on a more technical levels, that they really have to fight losing the atoms from the trap and so on and so forth.
You have to make sure you have all the states.
Yeah, so one of the aspects which I didn't emphasize is that this spontaneous emission model that we have there is actually also a model for an open quantum system and coupling to the environment. And so what we can basically do there is we can, by varying the mode density, we can vary the spectrum that is available for losses, and thereby we can sort of modify strongly what decoherence rates and loss rates are. And something that we have not yet exploited is we can also seed the vacuum. So right now this is of course empty, but we can put particles in there at some temperature and then study the interaction of our small quantum system with that reservoir. So that's definitely something that's also very hard theoretically and not so hard experimentally maybe.
Okay, thank you. Are there any further questions? It's somewhat difficult from here to see. You can see us very well, but we can barely see you. So, let's.